Hi everyone. So in this video we discuss locally connected layers, which are basically a generalization of convolutional layers that maintain the feature of sparsity. So unlike fully connected layers, here every output unit is connected to only a subset of local input units, but it doesn't maintain or it doesn't have the feature of parameter sharing that convolutional layers have. So basically, for locally connected layers, all the parameters connected to one unit, right, are different from the parameters connected to any other unit, right? So if I have, let's say, kernel size of width 3, right? So this unit has, let's say, WA, WB, WC, right? The next unit will have WD, WE, and WF. Right? So all the weight parameters are different. So what's the difference here? So obviously you have many more parameters, right? So for a locally connected layer with a number of units equal k, let's say a number of units equal x and a kernel size of k, you would have k times x weight parameters. But for a convolutional layer, you would have only k weight parameters, right? So here there is no sharing of the weight parameters, but we still have sparsity. So obviously there is more computation because there are more parameters, right? And the model is more complex, but it's also more flexible and can learn more things than a convolutional layer. So remember, here I could have a final solution where WD equal WA, WE equal WB, and WF equal WC, right? In the example plotted here. So I could, if you replace a convolutional layer with a fully locally connected layer, theoretically you can, the network can learn anything that the convolutional, that the network with the convolutional layer has, but it has more expressive power. Maybe it can also have more solutions. But of course, whenever you have more flexibility, that can come at a cost of difficult optimization and the possibility of you could have overfitting, like like less generalization, because you have more functions that your model can represent, and hence the model has a higher chance of custom tailoring to the training data. Now, a balance in between locally connected layers and convolutional layers is what's called tiled convolution. And tiled convolution basically involves defining a tile, and you have the same pattern as a locally connected layer, different parameters for the tile width, and then you repeat or you share parameters every tile as a convolutional layer would do. So for example, in the example plotted here, right, in that example, so this is an example with a tile t equal 2, right? So every 2 units we share the same parameters. So here WA, WB connected going out of the first unit, WC, WD going out of the second unit, and then you repeat WA, WB again, WC, WD again, right? So it's the same parameter WA that is here shared here and here, right? Instead of every unit, every 2 units. So this is like a trade-off between. So now let's try to think more high level, like how to design these layers. So when you have different parameters, right, it means that you're trying to detect something that spans multiple units, right? So you're trying to detect a feature, like for example, if you're trying to detect an eye for an image of a face, right? And so the shape of the eye spans multiple pixels, right? So this is a pattern that spans multiple input units, right? And that pattern is not detected just by one output unit that will fire, but multiple of the output units that should fire together, or that should form a pattern together, right? So think of it this way. if the feature you are trying to detect can be detected through only one output unit, then a convolutional layer suffices. But if you need multiple of these output units, multiple of lower level features to be detected together, then basically you need tiled convolution. If you need the whole layer to form a pattern that will fire together, then you need a locally connected layer. Sounds good? So you can think of the tile. So this comment right here is, I think, is very important. You can think of the tile as the size of a larger scale pattern that we want to detect, like the shape of an eye, for example. But you want to detect it with translational equivariance. That's why we repeat the same pattern when the tile ends, right? So here, every 2 units, for example, the bigger the tile, the bigger the pattern that you are trying to detect. But you still want to maintain the translational equivariance, meaning if the input shifts, then the output should shift, which greatly can enhance the generalization performance. Because if I detect an eye in a face for the training example, then if it gets shifted, I can still detect it in another face in the test images. Now, another important comment is that basically is related to applying pooling. So remember, convolutional, whether the convolutional kernel or a tiled convolution or locally connected layer, this is the first stage of a layer, and then you have the detector stage and then pooling, right? Now, when I apply pooling over different units that are connected to different kernels, like what happens in locally connected layer or with tiled convolution, then what pooling does is that it introduces invariance over the transformations that these different kernels are learning, right? So here, for example, this unit is connected to WB. So this unit right here is connected to WB and WC. This unit right here is connected to WD and WA, different weights, right? So if I apply pooling on the output of these 2 units, then pooling introduces invariance over these 2 kernels. One is given by WB and WC, and the other is given by WD and WA, right? So these 2 kernels now can learn the transformation over which pooling introduces the invariance. So remember the example when we said in the pooling video. So if I have an image of a 5, I rotate it by 45 degree or minus 45 degree. These kernels, one given by WBWC and the other given by WDWA, can learn the transformation over which the pooling applied over these 2 units can introduce the invariance, right? So this comment here is also, I think, is super important in the design of locally connected layers and layers with tiled convolution. Thank you.